Look around you. Chances are you are in a building. If you are in a modern city, that building is probably wrapped in glass. They sculpt our skylines. They connect us to the world outside, flooding our offices and homes with daylight. They are symbols of progress and modernity. But there is a hidden cost to all this transparency. Our beautiful glass buildings are energy hogs. They are trapping us in a cycle of consumption that is warming our planet and straining our power grids to the breaking point. Glass, for all its aesthetic appeal, is a terrible insulator. Think of it like a leaky bucket. In the searing heat of summer, that glass lets the sun's warmth pour into our buildings. Our air conditioning systems then have to work overtime, chugging down enormous amounts of electricity just to keep us comfortable. Then, in the cold grip of winter, the same glass lets the precious warmth we generate inside escape out into the chilly air. Our heating systems must burn fuel or use electricity relentlessly to replace that lost heat. This constant, inefficient exchange makes our glass-clad skyscrapers some of the most energy-intensive structures ever built. You might think rooftop solar panels are the answer, and they are a piece of the puzzle, a good start. Look at a tall building. A 50-story tower has a relatively tiny roof compared to the vast, sprawling surface area of its four walls. To understand this revolution, we first need to rethink what we mean by sunlight. When you look at the sun, don't actually look at the sun. The light that reaches your eyes is just a sliver of the total energy it beams down to Earth. Sunlight is a broad spectrum of energy, a rainbow of different wavelengths. Our eyes see a narrow band called visible light. This light gives us reds, blues, greens, every color in between. It lets us see the world. But so much more energy arrives unseen. Beyond the violet end lies ultraviolet, UV. It is the high-energy radiation that gives us a sunburn. Beyond the red end lies a vast ocean of near-infrared, NIR. You cannot see it, but you can feel it as heat on your skin. Astonishing fact, about half of sunlight's energy is in the near-infrared. A smaller but significant portion is in the ultraviolet. All that energy is passing through our windows, heating up our rooms, and going completely to waste. It's an unseen harvest waiting to be gathered. Transparent solar glass is simple. Let visible light pass through, capture the invisible parts. This is spectral selectivity. So how do we actually build these magical windows? The science is rooted in the field of organic photovoltaics, or OPVs. Unlike traditional silicon solar panels, which are opaque and rigid, OPVs are based on carbon-based molecules, flexible, lightweight, tunable. Scientists can design these molecules to absorb very specific wavelengths of light. Donor molecule, acceptor molecule. When a particle of UV light, a photon, strikes this active layer. When a particle of NIR light, a photon, strikes this active layer, it excites an electron, creating a little packet of energy. This packet then travels to the boundary between the donor and acceptor molecules, where the electron is freed to move. This flow of electrons is, by definition, an electric current. To collect it, transparent conductors are placed on either side of the thin organic layer. Indium tin oxide. Silver nanowires. When sunlight hits the glass, the organic layer absorbs the invisible UV and NIR photons, electrons start to flow, and the transparent conductors whisk them away to power the building's lights, computers, air conditioning. It is an elegant microscopic dance of photons and electrons, all taking place inside a seemingly ordinary pane of glass. A major breakthrough in this field has been the development of something called non-fullerene acceptors, or NFAs. For a long time, the acceptor molecules in OPVs were based on a type of carbon sphere called a fullerene. But NFAs are a new class of molecules that give scientists far more control. They allow for more precise tuning of which light gets absorbed, leading to better transparency and higher efficiency. They are also more stable and durable than older materials. As of today, in 2026, lab-scale cells using NFAs have reached efficiencies over 19%, and large-area commercial modules are now being certified at around 12.6% efficiency with high transparency. That is a game-changing number. This level of efficiency means that a significant portion of a skyscraper's facade can become a meaningful power source. Consider this. A typical office building uses about 150 to 250 kilowatt hours of electricity per square meter per year. A solar glass facade with 10% efficiency in a reasonably sunny city could generate 30 to 50 kilowatt hours per square meter per year, or even more. When you multiply that by the thousands of square meters of glass on a high-rise, you start to see the potential. Many buildings could get close to generating all the power they need on-site, a state known as net zero energy. When we think of solar power, we instinctively picture panels tilted up at the sun on a rooftop. But in a dense city of towers, the vertical surfaces, the walls, have surprising advantages. The first is geometry, especially in cities far from the equator: London, New York, Tokyo. The sun spends much of the year at a low angle in the sky. For months, the sun's rays strike vertical walls more directly than flat roofs. Vertical solar glass can generate more power during winter months, precisely when buildings need more energy for heating and lighting. Then there is the city itself. Urban environments are landscapes of reflection. Sunlight bounces off everything. This reflected light is called albedo. A vertical solar window can capture light from the street below, from the shiny facade across the way, from clouds. In winter, snow-covered ground dramatically increases albedo, bouncing extra sunlight onto building facades, significantly boosting their power output. Rooftop panels mostly just see the sky. Vertical panels see the whole urban environment, giving them more opportunities to harvest scattered photons. Vertical surfaces also have a maintenance advantage. They stay cleaner. Rooftop panels accumulate dust, grime, bird droppings, snow. That soiling can reduce efficiency by 10% or more and requires regular, costly cleaning. Vertical glass walls are naturally cleaned by rainfall. Snow does not accumulate on them. Dust has a harder time settling. They maintain higher performance over time with far less upkeep, important when managing a 60-story power plant. This reliability is key to making the economics work. Let's do the math for a 50-story building. Its roof might have an area of 2,000 square meters. Its 4 walls could have a combined surface area of 40,000 square meters. That is 20 times more available space. Even if vertical glass is slightly less efficient per square meter, the vast area means total energy generation is orders of magnitude greater. By going vertical, we are tapping into the largest and most underutilized real estate in our cities, their skins. 2 paths to power: retrofits and new builds. So how do we get this technology onto our buildings? There are 2 primary pathways forward: one for the cities we already have, one for the cities we are building. The first path is retrofitting. The vast majority of the buildings that will exist in 2050 are already standing today. We cannot just tear them all down. For these existing glass towers, the solution comes in the form of thin, transparent solar films. These films can be manufactured in large rolls and then applied directly to the inside surface of existing windows. It is a relatively quick, non-disruptive process that can transform a decades-old building into a modern energy generator. These retrofit films are a powerful tool. Current versions offer effective efficiencies in the range of 7% to 9%. While that is lower than factory-integrated glass, the return on investment can be very fast. The film does 2 things at once. It generates electricity, and by blocking infrared heat, it dramatically reduces the load on the building's air conditioning system. In many hot climates, the energy savings from reduced cooling can be even more valuable than the electricity produced. For building owners facing new carbon taxes, like New York City's Local Law 97, Retrofitting with solar films can be the fastest way to cut emissions and avoid massive fines. The second path is for new construction. For buildings still on the drawing board, we can integrate the solar technology directly into the building's facade from the start. This is done by creating factory-sealed curtain wall units, where the active organic photovoltaic layer is laminated safely between two panes of glass. This integrated approach offers higher efficiency, reaching that 12.6% mark and beyond, and greater durability, with expected lifespans of 25 years or more. It allows architects to design the building as a holistic energy system from day one, optimizing every aspect for performance. Architects can choose different levels of transparency and tint for different elevations of the building. Perhaps a darker, higher efficiency glass on the sun-drenched south facade and a clearer, lower efficiency glass on the north side. The glass is no longer just a passive skin. It becomes an active, dynamic part of the building's metabolism. As the cost of this technology continues to fall, it will soon become standard practice, as essential to a new skyscraper as its foundation or its elevator system. Every new tower will be born as a power station. Generating power is only half the battle. The sun does not shine at night. It can hide behind clouds during the day. For solar glass to be truly revolutionary, it needs to be paired with energy storage and intelligent controls. This is where the concept of the building as a battery comes in. Each building does not just generate power, it stores it for later use. This can be done with compact battery systems located in a basement, or even smaller distributed storage units placed near the windows themselves. This allows a building to capture solar energy during peak daylight hours and deploy it during the evening or on cloudy days. With on-site storage, a building achieves a new level of energy independence and resilience. It can operate off-grid for periods of time, protecting its occupants from blackouts caused by storms or grid failures. But the real power comes when we connect these intelligent buildings together. A network of solar-powered, battery-equipped buildings can form a local microgrid. They can share and trade energy with each other. If one office building is generating more power than it needs on a sunny afternoon, it can send that excess power to a neighboring residential building where people are starting to come home and turn on their appliances. These are sophisticated software platforms that act as the building's brain. Using artificial intelligence, they analyze data from weather forecasts, electricity price signals from the grid, and real-time occupancy patterns within the building. The system can then make intelligent decisions. For example, if it knows a hot, sunny afternoon is coming, it might pre-cool the building in the morning when electricity is cheap, then let the temperature drift up slightly in the afternoon, while the solar glass is exporting maximum power to the grid, earning the building owner money. This network of microgrids fundamentally changes our relationship with the central power grid. Instead of a one-way street where massive, distant power plants push electricity out to passive consumers, the system becomes a dynamic, two-way exchange. The city's buildings become an active, distributed resource that helps stabilize the entire grid. During a heat wave, thousands of buildings can simultaneously reduce their consumption and export stored solar power, preventing the need to fire up expensive and polluting peaker power plants. The city itself becomes a resilient, self-balancing energy ecosystem. The impact of transparent solar glass extends far beyond just generating electricity, It can fundamentally improve the quality of life in our cities. One of the most significant co-benefits is the reduction of the urban heat island effect. Cities are often several degrees hotter than surrounding rural areas. Dark surfaces like asphalt absorb and radiate the sun's heat. Rooftops and roofing materials do the same. Traditional glass windows contribute to this by letting infrared heat pass through into buildings. That forces higher air conditioning use, which then pumps even more waste heat out into the streets. Our cities are cooking themselves. Solar glass breaks this cycle. It absorbs the invisible near-infrared light, preventing that heat from entering the building in the first place. That directly lowers the need for air conditioning. saving energy, and reducing the amount of waste heat dumped into the urban environment. Multiplied across thousands of buildings, this can measurably cool an entire city. Studies show cool facades that reflect NIR light can lower ambient city temperatures by several degrees Celsius. Studies also show facades that absorb NIR light can do the same. This creates a positive feedback loop. A cooler city means every building uses less energy for cooling, leading to further reductions in waste heat. Another profound benefit is land conservation. Today, powering our world with solar needs huge land areas. Large utility-scale solar farms require vast tracts of land. A 1 gigawatt solar farm can cover over 10,000 acres. That creates conflicts with agriculture, it threatens wildlife habitats, and it impacts natural landscapes. Vertical solar offers an alternative, using the surfaces we already built. Cities contain billions of square meters of vertical glass. Tapping this means huge clean power without clearing forests or farmland. Generating power where it's used is far more efficient. Transporting electricity long distances loses 5 to 10% as heat. That's a colossal waste. On-site solar glass generation virtually eliminates those transmission losses. Electrons are generated at the window and travel just a few meters to a light fixture, or to a computer. This efficiency saves money and reduces the need for expensive new high-voltage lines, making the energy system more robust and cost-effective. For any new technology to succeed, the numbers have to work. The good news is that the economics of transparent solar glass are rapidly improving. The cost to manufacture these materials is falling due to economies of scale and innovations like NFAs. We measure the cost of power using a metric called the levelized cost of electricity. It represents the total lifetime cost of a system divided by its total energy production. The LCOE for building integrated photovoltaics is now approaching parity with retail grid electricity prices in many major cities. That makes it a financially viable investment. What really tips the scales is policy. Forward-thinking cities are putting a price on carbon emissions from buildings. New York City's Local Law 97 took effect in 2024. It sets strict carbon emission caps for large buildings and imposes heavy fines for exceeding them. For a building owner facing fines of hundreds of thousands per year, a solar glass retrofit becomes a smart financial decision. The payback period can shrink to under 10 years, driven by energy savings and by fine avoidance. We must ensure the benefits are shared equitably. A landlord could sell power back to the grid while tenants still pay high bills. Policies must address that. One solution: virtual net metering, crediting solar value directly to tenants' accounts. Another: community microgrids, bringing residents, including nearby affordable housing tenants, into part ownership of the local energy system, sharing in the profits and sharing in the resilience. We also have to manage public perception. Some worry solar windows will be dark, discolored, or produce unpleasant glare. But spectral tuning makes them virtually indistinguishable from high-performance architectural glass. They can maintain high visible light transmission and clarity, preserving a bright, open feel. Showcasing successful early projects and communicating the science clearly will build public trust and excitement, so the tech is seen not as a compromise but as an upgrade to our urban environment. The science is clear. The technology is here. The path forward is lit by an invisible spectrum of sunlight. Transparent solar glass offers a future where our cities are not just consumers of energy. They become producers. Every skyscraper becomes a silent vertical power plant, cleaning our air, cooling our streets. This is not a distant dream. It's achievable by 2030, if we act now. Responsibility falls on city leaders, building owners, architects, engineers. First, scale up manufacturing. Governments and private investors must fund factory expansion. Non-fullerene acceptors, transparent conductors. Mass production will cut costs and unlock access. Move from boutique to industrial scale. Solar glass, as common as steel and concrete. Second, standardize rules of engagement. Cities and utilities must coordinate on simple, uniform interconnection rules. Complex, inconsistent rules add delays and costs. Standardization will accelerate adoption and unleash private investment. Third, expand bold carbon pricing policies. Laws like New York's Local Law 97 send market signals. More cities need similar building carbon standards. That will drive billions into deep retrofits with solar glass at the center.